Hello and welcome to the first video of the FP2 chapter, Polar Coordinates. On the screen, just running through the basic concept of where this chapter grows from. How can we describe the position of point P? To describe the position of P, we need a reference point. Usually this is the origin. And you're used to seeing Cartesian axes, x and y, like this, and you go along the x-axis so far and you go up the y-axis so far, and that gives you the position of point P. But that's not the only way you can describe P with a reference point O. Instead of this, you could use a single initial line and ask how far around in a circle going counterclockwise from that initial line is P, and then how far out in terms of an absolute distance or a radius of the circle going around like that. So that's where this is coming from. We've got Cartesian coordinates x and y, and polar coordinates, the radius, how far out from O, and the angle from the positive x-axis, which is what you're used to this being, but we're going to start calling it the initial line for polar coordinates. The initial line just means where the angle theta is going to be 0, where we're going to measure theta from. So an overview of this chapter. In the textbook there are only 4 sections, but I've split them up a little bit. The first section in the textbook is these two. We're going to interpret polar coordinates and convert simple polar functions into Cartesian equations in this video. We'll continue that in the next video with harder polar functions. Then we've got to sketch polar curves, determine horizontal and vertical tangents, which is the last section in the textbook. And then we'll come back to the third section in the textbook to calculate the area under polar curves and the area between two polar curves. And that will be this FP2 book finished. So let's have a look at polar coordinates. In Cartesian form, as we've said, y is equal to the function of x as a function where x is the horizontal distance along the x-axis from the origin, and y is the vertical distance along the y-axis from the origin, and we write that as x, y in brackets. You're very familiar with that, you've been doing that for years. By contrast, in polar form, r is equal to a function of theta is a function where theta is the anti-clockwise angle from the initial line, which is similar to the positive x-axis in terms of how it looks on the diagram, and r is the distance from the pole, which is the origin, usually. And we write that in a very similar way. Instead of x, y, we write r theta. So just a few quick examples of that, how you might see this written. Here we have point P. If each of my circles here indicates a unit of 1, then this has a radius of 3, and the angle going around from theta equals 0 here, anti-clockwise all the way around to 2 pi back at 0, then this would be pi by 2, pi, 3 pi by 2, 2 pi or 0. And if this is pi by 2, then this must be pi by 4. So our coordinates here for P is r is 3 and theta is pi by 4. Q here, the radius is 2 and the angle is pi by 2. Keep going around and put r here, the radius is 1 and the angle here is 3 pi by 2. And finally, S over here, we've got 1, 2, about 2.5 here. And then the angle, if these lines here are giving us a quarter pi each, then half of that must be an 1/8 pi. So we've got 2 pi minus 1/8 pi gives us 15 pi by 8. So we've got a radius of 5 over 2 and an angle of 15 pi by 8. Now converting between polar coordinates and Cartesian coordinates is fairly straightforward because we kind of already know how to change between x, y and r theta if I put on our usual right-angled triangle here. You know this is y and this is x. This angle here is theta and this distance here is r. That's just a very simple right-angled triangle. You know that x squared plus y squared is r squared, and r cosine of theta is x, r sine of theta is y, and the tan of theta is y over x. So the key relationships between these four things are these four relationships here, which you're already familiar with. And these are the things we're going to use to help us convert between polar equations and Cartesian equations. But a quick side note here, why use polar coordinates at all? Well, simple answer is that some functions are easier to write in polar form. Some functions are much easier to write in polar form. But a simple example here, r equals 2, that's a very simple equation, and that means that r, the radius, is 2, so we get a circle of radius 2 centered on the origin. That in Cartesian form is not very complicated, you know how to do circle equations, but it's certainly more complicated than this. So circles with a center at the origin is just r equals some constant a. We also have theta equals 3 pi by 8, so if theta is equal some constant angle, then that's a line going up, out like this, a half line, and to have that in Cartesian form, again, it's not very complicated, especially if this gives you a nice number, but it is more complicated than this, especially needing this little tag on here to make it a half line rather than a full line. So the equation of a half line, theta equals some constant alpha. These are two quick examples of how much simpler some equations can be in polar form. When we get to sketching polar curves, you'll start to see some of the equations that we have in polar form giving us curves that you just can't write with a Cartesian equation at all. So this is the key reason why some functions are easier to write in polar form, some functions you just can't write them in Cartesian form. So using these relationships, we're going to convert some simple functions to find out what they represent, because at the moment you're probably very familiar with lots of Cartesian equations and you're not very familiar with their respective polar form. So we're going to have a look at a few and show you what they are. To do this, it's often helpful to get r squared as part of your manipulation, because if you can get r squared, then you can just substitute that straight away for this. And it's also very useful to get r cos theta or r sine theta for the same reason. As soon as you get this or this, you can substitute straight away for x and y respectively. So although they do get a lot more complicated than this, and we'll talk about that in the next video, for now, some simple polar functions to convert. Here we've got r equals a cos theta. So we've got a cos theta, that's great. We can use that to get an x, but I don't want to put x divided by r. What I want actually here is to multiply this whole equation by r to give r squared equals ar cos theta. And I realize that's pretty much the same thing, but I can see now in one go that this will become x and this side will become x squared plus y squared. So we get x squared plus y squared is equal to a times r cos theta, which is x. So we have this. Now it might still take a bit of manipulation for you to see exactly what this is going to look like, but we can do this. We've got x squared minus ax plus y squared equals 0. Now if we complete the square, we can have x minus a over 2 squared minus a squared over 4 plus y squared equals 0. Bring that on the other side and we get x minus a over 2 all squared plus y squared equals a over 2 squared, and I'll write it like that because this is our r squared. So we can see that r here is a over 2, and the x coordinate of the center point is a over 2 as well. That means we have something that looks like this, where the center point is at a over 2, the radius is a over 2, so it cuts here at a and here at the origin. So r equals a cos theta is a circle with center a over 2, 0, and radius a over 2. Our second one, r equals a sine theta. You can probably see where this is going to go. We've got everything multiplied by r to give r squared there, and r sine theta here. So again, we've got x squared plus y squared on the left, a times y this time on the right. And we're going to do the same thing. Take that over here and complete the square. And then take the a squared over 4 back on the other side. Make it clear that that's the radius squared. Write it like this. Very similar situation then, except now we've shifted up the y-axis instead of the x-axis. So r equals a sine theta is a circle with center 0, a over 2, and radius, again, a over 2. The next one was r equals a secant theta. This is obviously going to be a little bit different. Let's see what happens if I write this as a over cos theta. And then it's going to be really easy to get this r cos theta if I multiply everything by cos theta. And then as soon as I've got r cos theta, I should be looking to change that into an x. So this just becomes x equals a. And this is one example where you can see obviously it's easier in Cartesian form. It won't always be easier in polar form. And this gives us a vertical line through a. The final one of the 4 that was on that screen, r equals a cosecant theta. And again, you can probably guess where this is going to go before we do it. This is a over sine theta. Take that on the other side. R sine theta equals a, replace that with a y. Y equals a is a horizontal line through a. So there are a few examples of some very simple polar functions, changing them into Cartesian form. I have a slightly more complicated example to finish with, and then we'll look for the next video before we do the exercise. The curve C has polar equation this, and we know what that is now, we just did that, with this angle here, and the line D has polar equation this, and this is the angle here. First part of the question, find a Cartesian equation of C and a Cartesian equation of D, so we're going to have to do pretty much exactly what we just did, but with numbers instead of A, and sketch on the same diagram the graphs of C and D, indicating where they cut the initial line. Remember, the initial line is effectively the same thing as the x-axis. The graphs of C and D intersect at the points P and Q. Find the polar coordinates of P and Q, so we need to find where they intersect. But let's start with this first one here. Find a Cartesian equation of C and a Cartesian equation of D. So we've got r equals 6 cosine theta, multiply both sides by r, specifically to get r cosine theta, and then the r squared is a nice easy consequence that we can change into x squared plus y squared. 6 times r cos theta is x. Take that 6x on the other side and complete the square, gives us x minus 3 squared plus y squared minus 9, bring that 9 back on the other side, and we have a circle equation for C. For the line D, we've got r is equal to 3 secant pi by 3 minus theta. That is 3 over cosine of pi by 3 minus theta. So if I bring that up, r cosine pi by 3 minus theta equals 3. Now if I split that up using the addition formula, we get r times cosine of pi by 3 cosine theta plus sine of pi by 3 sine of theta. Now what I'm going to do is expand this bracket, so the r is going to come with the cosine theta and with the sine theta, so r cos theta will give me an x, r sine theta will give me a y, and I'll also evaluate cos pi by 3, which is a half, and sine pi by 3, which is root 3 over 2. So doing those things together gives me a half r cos theta plus root 3 over 2 r sine theta equals 3. I can multiply everything by 2 here to give me a 6 here instead, and then r cos theta is x, and r sine theta is y. So we're going to have x plus root 3y equals 6. I'm tempted to leave that how it is, but actually, because I know I'm going to sketch it in a moment, I will rearrange it into a more familiar format. I'm going to put root 3y equals minus x plus 6, divide everything by root 3, and rationalize at the same time. So we've got root 3 over 3 minus x plus 2 root 3. It might be worth mentioning that they do of course have a limited domain, both of these, in polar form. And I don't know yet whether I need to limit the domain of these two in Cartesian form, and to decide on that I will probably sketch them and see if any of my sketch falls outside of these areas of the graph in terms of the angle. But seeing as the next thing I'm going to do is sketch them anyway, I'll move on, I'll sketch it, and if there's an obvious limitation that should be put onto these, I'll try and remember to come back and put that limitation on these equations. So although I haven't put it on here, keep in mind that there might be some limit to the domain in Cartesian form if there's a limit in the polar form. So sketching these two, we've got a circle here and a line here. Get up a graph. To sketch these, I'm going to be thinking in terms of Cartesian coordinates, x and y, even though my question is asking me about the initial line. I know that the initial line is the same as the positive x-axis. But I know how to sketch these in Cartesian form more easily than I do sketching them in polar form. So looking at the circle here, we've got a center point at 3, 0. Let's put that in yellow. And it's got a radius of 3, square root of 9. So that's going to come up to 6 and down to 0. Up to a 3 and down to a minus 3. So it's going to come round something like this. That wasn't too bad. Now the line in purple, we've got a negative gradient that's approximately a half and a y-intercept a little bit more than 3. So we've got here 2 root 3, negative a half, it comes down. If y is equal to 0, x is equal to 6 from the form we had on the previous screen. So that also will go through 6 here. So it looks something kind of like that. Now the limits I had in the question, for the curve C, we had the angle had to be between minus pi by 2 and pi by 2. So from the initial line, minus pi by 2 is clockwise down to here, and pi by 2 is here. So it's on the right-hand side of the y-axis, but it's all on that side anyway. So I don't need to limit my circle. The line goes from minus pi by 6, which is somewhere down there, to 5 pi by 6, which is somewhere over here. And somewhere down here there might be a point at which the line stops because of this limit, but I'm not going to worry about that. What we're going to do is move straight on to part C, which asks the points P and Q, the intersection points, where are they? And before I go onto that screen, let's just note that x equals 6 is a point of intersection. We can see that very clearly on the graph here. We know that this is 6 on both curves, so this is one of the intersection points. This one might be a little bit harder to find. So we know one of the answers should be x equals 6 when y equals 0. So let's go through the process and we can double check our answer at the end by confirming that this is one of them. So we've got this equation and this equation, or we could use this equation and this equation. Again, I'm a bit happier using Cartesian equations, as you probably are as well. So I'm going to find the solutions doing this, and then at the end, change what I've got into polar coordinates P and Q. Given that we know y is equal to this, I can square all of that to get y squared is equal to 1 over 3x squared minus 2x times 2, so minus 4x, and then plus 4 3 is 12. So if y squared is this, x minus 3 squared plus this, I can add on x squared minus 6x plus 9, and all of that has to equal 9 from this equation. Simplifying that gives me 4 over 3x squared minus 10x plus 12 equals 0. Put that into a form that's a bit easier to use. I'll multiply everything by 3 and divide everything by 2. So we get 2x squared minus 30 over 2 is 15x 6, 3, 18. And I know one of the answers is a 6, so that helps me to factorize. And this must be 2x minus 3. Double check that works. We get 2x squared minus 12 minus 15x plus 18. Yes, this works with this solution as one of the answers. So we've got x equals 6, y equals 0, or x equals 3 over 2, y equals 3 root 3 over 2. And if we use our previous relationships to change these into polar form, x squared plus y squared equals r squared, that gives us r equals 6 for this one. And we know that at that point it was on the x-axis, which is the initial line, so theta equals 0. And if we use x squared plus y squared here, we get r is equal to 3, and theta is equal to the inverse tan of y over x, gives us pi by 3. Double check, of course, that these are within the domains of the original functions. They are, so we're okay. Double checking as well that we haven't ended up with a negative radius. We haven't, we're okay. So p, 6, 0, and q, 3, pi by 3. To avoid having a really long video, I've cut this off here. So although you could have a try of the questions in the textbook, it'd be a bit of a challenge at the moment, but you could have a go. I would recommend watching the next video first. Maybe I'll see you there.